you can visit later on at any time, but I thought that it is better you have a relaxed seat and then you see the live demonstration. And if you have a question, please raise your hand. Dr. Yerdi is here, so he will be addressing your all questions, even right from setting up the things. If you have any doubt, if you want to also talk about specific samples, specific type of coating, soft coating, to hard coating, whatever substrate or simple substrate alone, not substrate, sorry, the material alone, everything is okay. So please raise your hand. We'll just go to you and we'll take your call. Then
I will try to answer.
Okay. So Komal, I think we are almost ready here. So if you give a green signal, just put your thumbs up and we'll just open the bottle.
Sure, sure. So I think we can start it. Not an issue.
Yeah, that's okay. So we have Dr. Komal there over. So who is going to take the full page to reach you there with all the details. Along with that, Shomadip and Abhishek is there, who are your very close friends. So let's start it. Huh? Okay. Wish you will have wonderful session.
Thank you so much.
Okay, over to you, Komal. Yeah.
Thank you, sir.
Good afternoon, everyone. My name is Abhishek. Hope you had a great time during the keynote session. Hope you had a great time during the keynote sessions. Now we will be looking for this crash testing facility, which is present at NAC-2 IIT Madras. So basically here we have two facility. One is the RST, rivet test crash tester facility. And second one is the MCT, which is the micro combo tester facility. So we'll begin with the RST facility. First, let us see the key features of the machine here. It has a maximum normal load of around 200 newtons, load resolution of around 100 micronewtons, depth resolution of around 0.05 nanometers, and scratch speed, which varies from around 4.4 to 600 mm per minute. So as we have already seen in the keynote sessions that why this scratch testing is being done. So basically it is done to determine the adhesive strength of the coating, right? Now, in this particular RST machine, we have an indenter, which is the Rockwell C-type spherical indenter, as you can see here. We will look after this in more details later on. Basically, during the scratch test, this indenter is scratched along the coating surfaces, and simultaneously a normal load is applied there, which ranges from around a minimum load to a predetermined maximum load. And during this scratching experiment, different sensors like acoustic emission sensors and friction sensors is attached to it, which gives a in-depth knowledge of the different variation during the coating failure. Okay, this is all about the introduction to the scratch testing machine. Also, after the coating, we can determine the three critical loads, which is generally called as LC1, LC2, and LC3, which we will see also at what particular time we can call it as a LC1, and at what particular distance we can call it as LC2 and LC3. That we will see after the scratch testing experiment. Now, I would like to call Dr. Komal Jain, who is the application scientist at Anton Paar. Over to you, sir.
Yeah, thank you, Abhishek, for the introduction. I think you have already done part of my job by telling about reverse stat, but anyhow, we will go in full detail now. So this is what we call reverse stat scratch tester. So RST3 in short form. So as Abhishek has already informed, the maximum load where we can go is up to 200 newtons. So it's very good for our hard coatings where we will require a very high load to do the scratch testing and find the adhesion or say lifetime of the coatings. To coming to the machine component as such, we will start from right. So first of all, we have our acquisition system or CPU that's on back side. I think we cannot see because of monitor in front. Then here comes our main system, RST. So if we start from here, first of all, we have our stage here. So in RST, we have one moment which is software control, which is along this axis. Then along the x-axis, or we can say we have this manual controls to move the stage right and left. Then to move the head up and down, we have a knuckle screws on the side. By turning it, we can move our head up and down. So that helps us to initially bring indenter to close to the surface level for starting the scratch. And other than that, that is the place with the help of which we do our initial focusing to select the area where we want to perform the scratch testing. Now coming here on this particular instrument, we have two objectives options on this knuckle. So first of all, we have a 5x objective, and then we have a 20x objective to see clearly, say even in the inside of the scratch, to get more information clearly on the delineation and other things. Then on the back here, if you can see, we have this Rockwell indenter mounted. It's 200 micron, right? Yeah, 200 micron dia, and on this itself we have our acoustic sample. So from below, if you can see this cable coming, this is related to our friction module. So by this we can, even while doing the scratch testing, you can see friction sensor. So because of having friction sensor in a indirect way, you can even study the wear of the films while performing the scratch test. We will go in more detail when I'll show you the software feature, how we can do the wear studies also by just using the scratch testing. So on the side, if you see here, this red knuckle, this is basically to lock our Z movement, so that when we are doing the scratch testing or something does not move. Now let's move to our scratch testing software, and correspondingly we will discuss in more detail as we open. So the scratch testing software itself is this, a small scratch yellow thing with icon. So we will just open it. So this is very a clean, easy to use software which we have here. So first of all, if we want to do some sample, we have to find this position, or you can say the position, good surface where you want to scratch, or the area of interest. So we will be using this standard sample TIALN to do the scratch in our case. So we will be mounting it on our sample stage. Let me just open it. So our sample is mounted. We will just move this screw to make double sure that nothing moves when we are, say, go to high loads. This is very important. The sample mounting should be as tight and firm, especially when we have irregular shape of sample or those, because say we are going to topmost load to 200 Newton. If it's not properly formed, because we are at high load, sample can move, and because of that our measurement may not perform what we want to properly. It can get tilt at that high angles and all. So always make sure when we are doing the measurement it's properly tighted, and that's why we have a small screw here to make it further click. Now to start the measurement, this is the software. First of all, we'll do a new, we can do. So here we can group the name, say we have multiple batch or something, we can just group a name. So let me give it just a name, workshop session, say. Then like general client details and all, and if we want sample information like what's my substrate and all those things, we can add those also. Say for example steel, and I know my coating, we can add the coating here information, say ALM. Then say what process, thickness, these are just the information for user or during road port generation. So we know what our sample are, what its thickness and parameters. Then we click OK. So now our group has been created. So just to start the indentation process, first of all we need to, as I said, bring sample to the focus. So we click on this small icon which is basically says to start the indentation process. As if you see, it's saying tables are going to move because we have just opened. The X table will initialize a bit along this Y movement. So we click yes. The main purpose of this is to make sure that say sample is not touching indenter or objective, so that no damage to the instrument happens. We'll click yes because everything is far away, we can see. So if you can see now it's moving bit, so it's going to its initialize states. So let's wait for it.
This is not every time. So when you open the software for the first time, the system need to do the initialization, and you don't need to repeat every time.
Yeah. So in software option, we can see we have two options. Simple scratch, you just want to see the scratch and do with general basic parameters like start and all. We can click on simple scratch itself. Let's have a brief view how this looks. So we can see here we have again multiple options. So one is say constant. So if you want to check with the constant force, particularly how your coating behaves, we can apply a constant force itself and then specify to the length required and the speed which it want to do the scratch. Then we have an option of progressive, the most general one I'll say used. So we have initial load, starting load, then we have a final load which we want to do. Then we can control things like loading rate as per acquisition rate, like how many data points or speedily we want. The other thing is scratch length and same scratch speed. So if you see here, we have scratch speed at auto. So as per the other parameters, it will automatically set my scratch speed. Then there are further things required if you want to say coatings, how quickly my indenter should reach to the surface, at what forces it detects the indenter, all those things we can change here. And then you can see pre-scan reference. So the pre-scan is a option basically where we keep it checked so that we know what my sample surface looks like before doing the scratch. So the benefit of having this is, say we have a very rougher sample. So what it will do while doing pre-scan, we already in a way have scanned how up and down hills, or say if we have a curved surface, how what the curvature it is. Then accordingly, when we apply the scratch, because of the close feedback loop, our force will be maintained constant, which we want. We don't want that our force profile moves as per my curvature, because then we may have wrong readings and we don't know when exactly the peeling or delamination of our scratch happen. And this is especially important for curved samples like say machining tools where we have coating on that, because we want to see properly how along the curved surface or good my coating is in that. Then we will cancel. Now let's go back and have a bit view on what's under advanced options we also get. So in advanced option, we can see first we have a single scratch like before, and if we see here, there's the option.
We can test on curve sample. The DZ capture in RST is 1000 microns. So if you stay in 1000 micron, we can, but if this is more than 1000 micron, that will be out of range of our measurement.
Okay. So we can proceed, I think. So here, if you see, yeah, we have further options like in simple test, we didn't see these options. So this is what the new part in general we will say. Initially in single scratch itself, we have the pre-scan option, which I discussed. So generally when we are doing curved or rough sample where you really want to know surface profile and don't want any error, it's always we should have this selected. Then if we see here, we have another option called post scan. So post scan is, now we have done the scratch, it again scans the surface area to see, say this helps us to get the residual depth, or say for example you have developing something called self-healing material, you want to say how much your area relax backs, your depth of resolution. So to get that idea, we will need to use the post scan. So we can time it also like after in more advanced way, that after this time it should do the post scan, so that we know how much it is healing or relaxing back our coatings. Then again at lower portion, which we saw in the simple scan, we have the same things, three type of load applications: constant, progressive, and other was, I think we missed it, incremental. So it's in a way of step. So stepwise we can apply the load to see how things change. Then here is the same options which we have in simple scan here. Then we can see in analysis it says optical analysis panorama. So that is basically after we do the scan via microscope, we do a panoramic image. We see along the scan, take various photos at different position. Software stitches those position, and we have a proper one-to-one relation between the signals which we were getting from different sensors like acoustic sensor, friction sensor, all those, and image to more, you can say, accurately and correctly we can determine the delamination or LC1, LC2 crack points in the system. Then here we have the sensor which is the acoustic sensor. So acoustic sensor is like, as it says, it's like sound waves passing, and via that we check out what the depth or how the depth is changing in the sample. So these sensors basically help us in the where, say, we are not able to clearly see the, say, cracking point or delamination point because, say, substrate and coating contrasts are not good. That is where these sensors really help, because whenever the, as the things change, we will see a corresponding changes in the sensor signal, and that signal help us to mark again our LC1, LC2 and LC3 correspondingly. Then we have this multi-pass scratch option. So again we can do multiple scratch to do how the, say, we want to do wear testing. We on a same track we can do multiple scratches and see the things, how the film is wearing off in that. Then we, and this we can do bidirectional, say not in one direction itself, we can say we have moved forward, then we can in same way while coming back we can do scratch in that way also. Then comes multi post scan. So this is where, as I told initially, the post scans importance. So if we want to see what's the recovery of my film area, and those are, that's where we do these options. So we can increase number of post scans to see, say, how many after this much time, how the recovery is happening. So we can determine, say, if self-healing material coating. So we can determine, yes, how good our self-healing coating is working in the area. So let's start with the simple scratch itself. So let's start from, let's go to progressive scan, and let's do a very small scan, say 3 mm. And let's do a bit fast scratch speed, say 5 mm per minute in general. And here you can see other option which we missed is the rock indenter. So be careful that correct indenter is always chosen here. Then we click OK. So it says sample is going to move the indenter. Yeah. Okay. Yeah. So here one thing we discussed, we missed the point is of foxing. Now if I just move, I don't know where it's going to scratch. So to do that, let's cancel it. First we will focus. Let's first do the foxing. So this is the foxing window which we can access by clicking this 4-headed arrows. So let's move sample back to the under microscope. So let's set it to 5x. So we move the turnet to 5x. So we are set. So we can see the window here. Let's set it to auto brightness. Let me resize it a bit. So we can have a bit. Yeah. So here we can control the movement of the stage along, because that's the only stage which is automatic. So we can control this movement by using our arrow keys left and right, And as I said initially, we don't have any movement, automatic movement along the Z. So to focus it, initially, first we unlock the movement. So we open this knuckle screw. Then from the side, we will now move our head up and down initially to get a view on the screen there where we can see. So I'll be going bit ahead the focusing point so that I have a leverage to move up and down later on a bit to do the more focusing. So you can see like the sample initially had some pre-scratch which is visible. Now I'm a bit out of focus. Now on here top, if you see, these are the adjustment which I have on hand here a bit. So I can do fine adjustment of microscope. If you see clearly, the head moves bit up and down using these screws. So that's why I'll go bit defocused area along Z, so I can focus and do the focusing more finely. Now I have selected my movement along the Z axis, so to be safer, I'll again lock it along the Z axis and we will do the focusing by using the dial here. It seems we have moved a bit extra down. So yeah, yes. So now we will look for a good surface area. Let me focus it. Yeah, this looks good. So let's find an area where we don't have a scratch, a clean area. So if you see here, we are moving the stage. By left, it's moving in that direction. And if I do the right one, it's coming towards me. So let's go. We have quite a few scratches. Then let's move it along the other axis and see finds a good area. Okay.
It is nice because you can do the movement of 3 millimeters and you can check the surface of your sample and then come back to the initial position. You can see if there is not any problem at the surface of the sample. You can select this area and perform the test.
So if you see like previously many.
DZ maximum displacement in DZ is 1 millimeter, 1000 micron.
That can be the maximum coating thickness it can sketch.
Yeah, 1000 micron is really the maximum thing that we can do. This is more than 1000 micron is not thick, it is not coating, is not really considered as
Sample.
no sample height. You can increase, you can open the red handle and increase the, you can go to more than, I will say 15 millimeter, 15 centimeter. Yeah.
It's always good that you just go and have a look, then you decide on your specimen and then you get it coated.
Yeah, but you can also remove the friction table and you can have more space.
So you can have your own fixture.
Okay, so we have found the area. Now thing is we have to select it. Yeah, this is my starting point, because then system will know when it's taking panoramic image from where to set. So to select the area, if we see it's mentions here in software also, press spacebar to take a new reference. So if you see here the software, we have a red dot and this line kind of shows where on the sample we are, red line. So if I press yes, you can see the dot has moved. So now my reference is set. Just to reconfirm what we can do, just click on the backlash and see if it is moves back forth and comes back. Yeah, this area is selected properly or not. Then we close the window. Now we have the area selected, so we can go with the scratch. So we will click it. We will do both pre and post scan to see how things look. And here is the scanning load for basically doing pre and post scan. So here initially we are doing, it's a hard coating, we know, so we can do at 1 Newton. So you have say bit of soft coating. Accordingly, we can change this load setting so that the pre and post scan generally does not harm my film sample. Basically, we want this load to be the limit where it does not scratches the film, and just we get a profile on the surface as such. So let's start. We'll keep what was by default itself, 1 to say 100 Newton. Then if we want, we know we have many samples on the same type of protocol and same measurement parameters we measure, we can just click save protocol to save that measurement parameters. To avoid inputting these things again and again, we can just open, select the protocol and run again, start the measurement for the other sample. Now let's click OK.
Komal, he can understand. He can. Yeah. Before I start the test, I prefer to increase the acoustic emission. That was 2.
Yeah.
The sensibility you can increase, and you can remove panorama. It's better to do panorama manually because you can have a good focus on the surface. Yeah. And increase to 7. You can select 7 for acoustic, 7 or 6.
Yeah. So we were keeping it to 7. So basically that is the sensitivity of our acoustic sensor. How highly sensitive to we want it to capture the things when we are passing the signal. So basically if you feel like you are not getting enough information from acoustic sensor, that is where we change this parameter. So it has value from 0 to 9. So we can put any value between this. So when we are at say higher side, that means basically we are making it more sensitive to the signal capture. We click OK. Then yes, it's same thing. It says sample is going to move under the indenter. So here's the thing. This pop-up, why it's important. You see now we had moved the head while we were focusing it. So because we don't have any z-axis automatic movement, it has to be manually up. So if I click yes, and by the way say we were very close or sample is big, it can stuck the indenter, we don't want, because that can cause damage. So this is the pop-up which reminds us to check the things again, that nothing will strike when table moves. So what we will do, we will unlock it, move the head up, so we are sure that nothing strikes. We'll close it, lock it again and click yes, because now we are sure nothing is going to touch each other and no damage will happen to the instrument. So you see now it is there, it says to adjust sample detector and clicks automatically. So basically what it means, generally we keep the indenter distance somewhere around 1 mm from the surface, and then the head moves down. So now we will bring the indent head down. For that again unlock the red by moving the red knuckle screw, and we bring the indenter down to approximately say the distance is around 1 mm between the sample surface and indenter. So we are pretty close. So we will again now lock it and we'll click OK here. And now it has started doing the measurements. So we can see the progress over top. Now here comes the thing, it is saying to do the finer adjustment for our depth sensor. So for that we have the knob here on the top. I think it may not be clearly visible because it's in like a groove thing, but we rotate it, and our aim is, so currently it is near yellow, this point, our aim is to get to the green zone. So we will rotate it. So we can see the location where we want to remove by this arrowhead. Basically it gives an idea in which direction we have to rotate the sensor to get to the our green zone. Yeah, so we are here, you can see there was an arrow which is gone now. So we click continue and our sketch test has started. So you can see indenter has made the contact, we can see, and we can see currently we are doing pre-scan and it is checking, and corresponding by looking above, we can find the things. Oscillations are coming.
The indenter just scan the surface to have the idea about the profiles with very low
Yes,
load.
so
So you
this
can
is
see
the profile happening.
the sample is just perfectly parallel. So we need to remove this part from the measurement.
Yeah. So now our scratch testing is going on. So here we can see the different signals coming here. So one is our applied node, one is our tangential force happening. This is my depth, penetration. So you can see here its axis, micrometer. This is along the length. So all the parameters while scan itself, we can have a view. So our scratch is done. Now it's doing the post scan to check the profile after doing the surface profile after scratching it. So by subtracting pre and post, we can get basically what's my residual depth is. So it's done. Now again, because now table is going to move under microscope, it's again saying make sure nothing collides. For safer side, I prefer to,
You don't need to change.
yeah, as such we don't need to, but say by the way, we have say 20x microscope which is bit lower side or those, so we prefer,
Okay.
you can say it's my habit, I'll prefer. So we'll just move it a bit, not too much, so that I am sure that nothing collides. The only thing downside is now we anyhow have to do focusing again. So it's near under the microscope. Now again we have to do it because of focusing. We are up, so we will come down to our scratch position, and you can see because everything is there, we are near to the scratch itself. So we can do fine adjustment by this smaller lobe, and coarse adjustment is via the bigger knob. So I will lock it. So here now by seeing the signals itself, we can mark our LCs by putting the markers from here itself. So we can move along the scratch to reconfirm from here itself view if our LCs are properly kept or not, or delamination has happened along the length. And if required, we want a panorama view.
Well, you can
Your voice broke. Actually.
perhaps you can have the better resolution of the tracks.
Yeah. So that's what he's saying. So what we can do, we can change the microscope a bit and let's focus again slightly. Yes.
Perhaps distance calibration is not good. So
Yeah.
you can come. Yeah, you can come back on in objective 5, please, and go to the end of the scratch.
Yes.
We'll go to the end of the scratch, and perhaps then you can find easily the.
Yeah. Actually, it's along the x-axis, which we don't have the automatic movement. Yeah. So we will have to move it.
Distance calibration is not good. Okay.
Yeah. So we will go a bit ahead in the scratch because here
check if you can find the scratch. Yeah.
Yeah.
Yeah. Okay.
It's there. It's because of contrast, so we can see the scratch itself. So if we want to move, we can see the track more clearly. Let me focus.
Here you can see the full delamination of coating.
Yes.
We reach to the substrate.
So by looking, we can see it's the initial track here. If we focus here, let's move to ahead, and you can see the small cracks appearing here. Let's go a bit behind. We have here also slightly, so we can mark somewhere here our first LC.
So the LC1 is when we can see the first crack, and after the crack will be repeated.
Yeah. So here are the fine small signals. So these are like the point for first LC. So we can click here, and my LC is selected. Now let's go ahead. And we can see here some fine delamination has started. So let's move a bit ahead. Yeah. So this is like my LC2, where starting second delamination or finer cracks has started. Now let's move ahead. So you can see the cracks are now becoming more and more big.
This is now we have chipping, and this is the cohesive chipping, because in this area we cannot see substrate, but you will see in some area here, for example, we start to see substrate.
Yeah. So
and then we will go to the delamination.
Delamination. Yeah. So we can see
you can perhaps adjust a little the light.
Yeah. Brightness. Yes.
Yeah, brightness, please. Yeah.
Yeah.
So nice. Now we can perfectly see the full delamination of coating.
Yeah. So from here we can see its delamination. Let's go a bit behind more. Also, so this was the cracks, fine cracks, which initially then the chipping. Yeah, chipping is getting bigger and bigger. And then we go here and we see the delamination happening, and we can see the bit part of substrate. So this is the point somewhere where we can mark our LC3 because delamination has started. Now if we come to our signals here, we can see the changes happening. So we could have marked using these also to our signal, because say flat, then we have a point of inflation that will indicate the LC1. So here we can see fine LC2. So this is how this, while seeing the signals itself also, you can mark our point of delamination. So this was a film where we still have a good contrast and we could see the fine cracks. So the case where say we are not able to have this kind of contrast, that's where by seeing these variations in signals, you can clearly mark your LC1, LC2, LC3. Now thing comes, if we want just optical and we want to take the panorama view, you see here it says grab panorama, or we can select a if we want from specific area to start taking the image, we can go to that image and click it, press start from that point. And let's go to the start as such only of the signal, and we will just click on grab. So what it will do, it says, have you set your focus correctly? Yes, we know. Remember one thing, we have now at 20x. So this image definitely is getting captured at 20x. If we want, we can capture images at different magnifications also to get more idea. Say initially we are not able to see the inside the track, but you want to focus outside, so we can initially take like on 5x, later we can move to 20x on that to go and see inside the track also. So let's
Focus is
click on,
manual in this case. Okay, we have
yeah,
another one. This is digital. The new generation is digital focus, but this one is manual. So during panorama, sometimes you need to adjust the focus. This is the old generation of the system.
yeah.
But in general, the focus is good because the system will keep you in mind the focus when the system do the pre-scan. And you have two methods to do the test. You can do the focus on the surface, or you can do the focus inside of the scratch.
So the depth of focus is shallow.
Yes, this is not too important. Depth of focus.
So it's done. Let's click next. No.
You need to wait.
Yeah, it's
the system will do it alone.
stitching. Yes. So basically what currently system is doing, we took use of different clippings. Now it's stitching all those clippings together. So we have exact proper scan, and then we will be putting our signals and everything top to each other. So let's say I am done with my optical analysis and all. We click finish. So we have only one water movement, so it should going something, say you want to do other scratch and you want to move away from there itself, so we can input a value. So by that amount the table will move, or we can simply cancel, say if you don't want to do any other measurement on the scratch itself. So now you can see we have our signal and we can change how things look. So we click on auto, now we have our scratch image on top of our signal, and if we want to further refine, we can move things and see and clearly see if we have marked or not. Say this was my LC1 point, so I can see some fine chipping happening earlier. So what we can do, we can remove my first optical here, and I'll put it where I could see first initial cracks happening. So I'll put it like this is my LC1. So in this way, after capturing the data also, we can refine our signals required. So we can see our LC2 is very good marked, where I could see the first chipping and then the delineation. So this is all about the, in general, the scratch testing part using RST3. We'll say.
I will just comment on it. Could you please show us the scratch panorama? I will just comment on this.
You want me to increase its size, right?
Can we see the scratch panorama?
Yeah.
No, we cannot see that. Well, I will see the panorama, the full panorama, please, on the top of the graph.
Okay, on the graph.
You have zoom on. Okay. Yeah. This is good. Okay. This is something that I will show you. This is the first scratch that we perform. We increase the load up to 100 Newton. Okay. But what is the aim of this scratch test? For us, we need to reach to the substrate. So you will see here, I cannot see perfectly, but about 50 Newton, we reach to the substrate, 50 or 60 Newton. If I have to repeat another time this test, I will never go up to 100. Because we know we will reach the substrate. If you go inside of the substrate, you just will damage your indenter. So you don't need, because you will use this method for several sample testing, not just for the one sample. So this is something that you need to know. You will first start to do the test. You will see the sample. You reach to the full delamination of the coating at 60 Newton. If you need to repeat the analyze, you will fix maximum load at 60 Newton. You don't need to go inside of the material. But if you don't see the full delamination, sure, you will try to increase the load to 120 to 150 to find really the full delamination of the coating. So this is something that you need to keep in mind. That you need to know what you will do with the test. If only first crack is important for you, you don't need to increase the load. You will stay at the range that only you can see the first crack. You can protect your indenter and you can use the indenter more for a long period without any problem.
So you have three loads now, like constant load, then progressive, then incremental.
Yes.
So according to you, in which cases we should use, means like when
this is really depends on the application. For example, this is the best method. For many of coating, we start increasing load, okay? But imagine you have the coating at, for example, at 20 Newton, your coating will be removed. You can say, okay, I know my coating at 20 milliNewton will be removed. You will fix constant scratch and you will do 20 Newton, 20 Newton, 20 Newton. If you have a sample that removed, that didn't remove, if your sample doesn't remove at 20 Newton and you need to increase the load, you will see this sample is different from the other batch. So perhaps you need to increase it.
So first we should do.
This is for fast analysis, okay? Or another thing is multipass. Multipass is nice because you can replace the indenter with a ball holder and you can do tribology test. So you can do the linear mode and you can move the sample and do the tribology test with the scratch tester.
Can you set an acoustic set point because I can see the similar.
Yeah, this is something that you can adjust. So I have selected 7 to be able to show you when you have the chipping, you can see the increase of the acoustic entry.
Set point. Okay, so when
This is important. Even you will see here, when you start to see the chipping, you can see the increase of the acoustic because the system will record the noise of chipping.
right. So when I can set it like a set point, you see the acoustic.
Yes, you can use it as if you need to use automatic analysis. You can say, I will use automatic analysis, and then you can see a drastic change of acoustic emission, select this area, or you can use it, for example, in the patient table.
So there'll be no chances of alignment. I mean, we are adjusting manually. We are placing the sample itself manually. How we are sure about the flatness of the sample, and also if you are applying load on one side, usually the other side of the sample tilts.
No,
Because
no, the sample Kumar, could you please show us sample?
Sure. You mean the sample?
Sample holder, the sample on sample holder. You will see here in sample holder. So we have prepared the L form. So the sample will be positioned on this L form area. So the sample cannot move. If the sample is moved during this is not good. It's very interesting in everything. So the penetration will change, so you cannot have a good data. The sample must be fixed. And sometimes this is a problem because some people try to do they prepare the sample in epoxy. And in some cases, if you apply 200 Newton, the epoxy will deform. So this is something that you have to avoid.
If it is a standalone, like only coating material also we can, I mean, if it is 200 microns or less, like 300 microns sample itself, then the issue will rise because, I mean.
300 micron, I will glue the sample on aluminum sample holder. You can use this super glue, you fix the sample, and then you can test. If you have a thin layer of sample, 300 micron, so you can never install 300 micron here. Because if you will try to tighten the screws, you will deform the sample. But you can glue the sample with super glue on a fixed sample holder, and then you can fix it. Okay?
Yeah.
It's okay, comment.
Yeah. So this is basically the aluminium sample holder. I think if you can see, they had pasted and done some measurement to keep it. So this is what Mohammed was taking. So if you have something, you can use super glue, put it here and do the scratch using that. So now I'll show you a other part. Now we have LC1, LC2. Similarly, let me put it auto. So say we can mark LC, LC1 based on our other signals, say acoustic signals, our friction modules, all those cases. So we can have slightly different LC1, LC2, but in general if we look at a good film, they should be almost similar. As we can see from here, when our chipping started, we have bit ahead in this signal rather than from point of deflation. So that's where combining all signals help us to get a more accurate idea. Then if we want the entire data as such in terms of analysis, say I values here are same, but say if I have done say 3, 5 something to check more thoroughly, that say the coating which I made, I want to check on the surface it's very homogeneous and along entire surface I am getting same LC1, LC2. So we do a statistical measurement and then we can look at the statics here itself, and then if we want to see the curves also measurement, we can see them from there by selecting different options. We can have result curves. Result curve means different variations in LC and all. So we can select accordingly. So you have, like you can see LC1 optical, we can have different say compare optical LC at a x-axis, and on y we can have other. So in this way we can have different modes in software also, that you can fully analyze your data, compare your data to come to your final decision and your regarding your data. So in general that's all what I think. Now we are done with the scratch testing. Now the other system which we have here is MCT, the micro combi test. I think Abhishek will introduce initially, Somik will introduce us, then we will proceed in similar way for the MCT.
Hello.
I was on mute.
Yeah, Abhishek and Shamanji.
Am I audible?
Yes, yes, very much.
So I'd like to thank Dr. Komal for giving us such an informative session about the scratch tester, the RST3 model. Now we have another module here, which is called the micro combi tester, also known as the MCT3. So as we all know, since this is a combi tester, we have the facilities of having both scratch as well as nano indentation, and some information about the machine. The load is not as high as that one, since the indenter that we use here is a Rockwell C 100 micron. So there we are using a 200 micron. But since the indenter here is 100 micron, the stress at the surface will be much higher, because of which the coating or the coating tends to fail at lower loads. So the maximum normal load of this machine is 30 Newton. The load resolution is around 1 micronewton, and the depth resolution is around 0.05 nanometer. Now for the nano indentation module, the maximum
Sir, hello. Sir, there's a message that you're not audible. Sir, would you mind picking
Your
up
mic
the
is-
other microphone, sir? You can take that microphone, sir.
Yeah.
You can take that lavalier microphone and you can use that microphone,
Yeah.
sir, please.
So it needs to be installed on a very sensitive anti-vibration cable. This machine is
Hello?
having already an inbuilt. Other one, we have already put it on a anti-vibration cable separately. But this NCT is already having an inbuilt anti-vibration. Otherwise, that's the resolution of 1 micron.
So as I was saying, now for the nano indentation module also, the maximum normal load we can go is 30 Newton. We have a...
From bit again, because they were not able to hear,
Okay, I'll start from the scratch again. So for the scratch, we have a Rockwell C indenter with 100 micron radius compared to the 200 micron radius. Here, I don't think it will be visible because of the balancing pin here. So we'll see where Dr. Komal will show you all the indenters also. And for the nano indentation module, we have the maximum normal load of 30 Newton as well. The load resolution is 6 micronewton and the depth resolution is 0.03 nanometers. Now I think in the keynote lectures, all of us have noted very carefully the importance of this load displacement curve for measuring the nano hardness or micro hardness of all thin films. So depending on the load, the load versus displacement slope gives you the stiffness from which and the penetration depth from which we can calculate the value of the hardness of the coatings. So this is all from my side. Now I'll request Dr. Komal again to take over the machine and help us with all the things that are left out. Thank you.
So please.
Hello. I believe my voice is audible, right?
As of now, yes.
Then great. Okay. So we'll again similar way have a bit brief overview of the system first. Then we will proceed to a sample, a demo nano indentation in this case, because basically we are scratch testing is same as we do here. The only thing is the difference, as Shomik has told, the maximum load we can go. By that scratch testing, I remember one thing which I should have told, like at a reverse state, basically with scratch tester mode, we can also measure conventional hardness required, because you can see we are taking we have the optical microscope and we are taking the images. So what we can do, we can create an indent and impression, then capture the image of the impression to get the optical hardness. So in case of RST, because maximum load which we can go is 200 Newton, so that is the maximum load we can do for conventional hardness on RST. When coming to MCT, for conventional hardness, we can go up to 30 Newton, because that's the maximum allowed load for scratch testing in the system. For nano indentation, in general, for basically I'll say instrumented indentation, we are at a load of 10 Newton, which we are limiting ourselves to. Then, as previously you already have things we have discussed, what's the difference between conventional during the morning sessions, and what's the difference between the instrument hard indentation. I'll be not going through that. So let's have a quick overview on the difference which we have from there in the asset setup also. Besides that, load range difference for scratch and indentation. So first of all, the system is mounted on a platform which we call 30001. So here, if you see, I have this platform on air cushions. So basically that is to help minimize our noise coming into the signal, because we are going to a very low resolutions. So we don't want any kind of noise coming into the signal to produce error in our measurement. Then the other thing here is our stage has both X, Y and Z movement. So there we saw we only have movement along one axis, but here we have movement along all three axes. So in that way it makes a life of the operator or user a bit simple also, because now we don't have to do unscrewing knuckle, move it up and down, see the position, and not that much worry about indenter and say our objectives or an sample getting collided, because of the having an automatic movement itself. So most of the time there are no chances that it collides, unless we have a very big sample which can cause that thing. So similar to there, here again we have our friction module. Here we cannot, I think, see, it's a plate here. So there we have our friction module. So we have all the data which we get there also for scratch. But when we do the indentation, we don't require the friction module. So we basically lock it, and this brass knuckle screw which we are seeing is one of the things which locks our mechanism. Then over here again the other thing is we have now our microscope, which is again automatic. So here the focusing, even we don't have to manually say move sample up or down, just as initially movement we have to do, and then system itself does the focusing also. So many, what will say, the user inputs or work has been reduced in there. Then can we come? So this is the optical microscope here, and then we have here is what our MCT head looks like. So here, if you can see, we have an option I and S, and inside is a small lever. So basically, by changing this lever, we initially move the position of the system from scratch to indentation. So basically what we are doing, we are removing certain sensor which does not take into the account, we don't require for scratch testing, like we don't require that much knowledge of depth sensing, so it takes it out of the picture. Then the other thing required is we change the indenter, like we saw for scratch generally we are using Rockwell indenter. So like here currently we have a Vickers mounted. So those are the main two processes which we have to do. Say we are switching from indentation to scratch or scratch to indentation was back. Basically we have to take care of friction module. So in scratch it's in work, so we take it out the knuckle screw and then we change the lever to scratch and change our indenter, and its opposite when we go for the vice versa. Now let me show, because you won't be able to see few things. I think you can see this part. Basically this is the reference ring. Now the advantage you have with this system in general, like conventional other indentation machines, generally they are on feedback loop. So you, what you are doing, you are first creating an indent, taking a feedback from that, and then move it the indent. So think what happens when you are doing an indent to get detect the surface itself. Basically we have already pricked the surface, so we have already done some damage to surface or say some that which we don't want, because that will act into the machine, and basically in other what we do, they pick that and do the via software we do that correction. But in that correction itself some error can occur. Say you have soft sample, in that case it may go more than what the correction has done. So having the benefit here, having the referencing first of all, is that we are detecting our surface in a way using the reference ring. So whenever I am detecting the surface, I know what my surface position is. So in first session you have clearly seen, if you can move, yeah, so you can see this ring here. This is basically the part of reference ring which goes on the sample and detects. Let's wait for it to get focused a bit. I think it's fine. Yeah. So this is the small ring. If you see, I am touching it. This is the reference ring. And then inside very small we have our indenter, which is the Vickers indenter here. So as I was saying, the thing is that when we have our surface, so when we do the indent, we know what our different H's are, because that is what by measuring we are getting our indentation value, like HC, Hmax and everything. We don't have any error. So there's the benefit that you are always sure, yes, the values which you are getting does not have any error and it's more correct, and you are getting what is actually the property of your film, your hardness of the film is. Now the other benefit also is, because of that we have this reference ring, it takes care of your thermal drift also. So say we have our frame, temperature is varying. In India we know it varies much during different weathers. So some expansion in frame and those happening, and when we are talking about nanoscale, those will give an error. So because it is moving, our reference ring is attached. First of all, it's not exactly matched to the reference frame, and then any thermal drift also happening, because we have a referencing ring, it takes care of everything. You are say frame expanding, thermal drift happening because of the indenters, contact and all those. So it takes care of everything and you purely get the data which is from your film. Now we will start with the reference measurement. So in this case we are using copper because it will be very easy to see the indent also in this case. So we will mount it. So we will see the jig system is similar what we have there. So let's mount it and again we will screw it up, and you see same way we have a small screw here to lock it further. So our sample is mounted. Now let's go to the system and open the software. So here our software is this blue icon one which showing small indent. For scratch we had this yellow one and showing. So let's click it. So again same intuitive, we have certain buttons over, we have down. So if we want to create a sample, basically let me move this a bit.
That covers up.
Yeah.
Rendered is about 8 millimeter and have the different size of the sensor. Have also the folder, so you the folder, and also the therefore you can measure for the general difficulty the COVID for RST 300 or RST 205, the value of both smart meters for MCD. 30 millimeter, 1 millimeter. This is spot, but normally 1 so 30 millimeter. 1
plus 1.
Okay,
13.
Not 1.3. It's 13.
13. It's not, but
You can. It's 8.
Okay, so in terms of
check any example, no, one check that.
can we proceed? Okay. So if we see software layout is kind of similar what we had for Scratch, just slight difference that we have another tab here, but if we look about above, things are very similar. We have this our safer position, it's automatic. ADO is automatic depth offset. So it is something we do initially to find the surface of indent where we want to do indent. So we do have an option to ADO before starting. We focus the area, we do the ADO, or we can, you will see later that we can do ADO during measurement itself also. So first screen is kind of similar. The only difference is if you see in sample here, there we have substrate layer option. Here we have substrate option also, but correspondingly we have Poisson ratio option. So thing is, as you know, Poisson ratio does affect our values. So we can select it from here, or software does allow us to edit these values later if required. So here I have a copper substrate sample itself. So I have selected copper and copper alloy only. So let's create another, give it a name, say workshop MCT, and OK. So we have this sample. Now we need to define our measurement. So we will be doing ADO during the measurement itself. So first of all is the foxing part. So here I don't as such if we want we can do foxing before also a bit like we did earlier, or it you will see it does show us all those window when we go for indentation also. So again like earlier we have first time opened the software, so you can see it is saying this thing. So it will everything will move to its initial positions like that, because first time we have operated, and if you look now, stage and everything will initialize and move to their position, then we will proceed. So it has initialized, and we can see now it's saying Wimple is going to move under the microscope, because we need to find a clear surface where we want to do the indent. So we click OK. So you can see sample is moving under the microscope. So here we have our microscope.
This is our digital microscope that I told you.
Yeah. So this is here the window. Now we have single window, left, right again, because we have Z movement also. So we have now movement along up and down. So if we talk about from keyboard, we can control this movement by using these arrow keys. These will take care of XY movement, and along Z we take care of that by using up and down. Similarly, we can make this movement fast, small by selecting corresponding options from here, or we can use plus or minus from keyboard also. Now, first we need to focus here. So what initially we will do, we will move it up. And if we want to make that movement even more faster, not just from here, we can do control and with that corresponding keys. So let's make this movement bit fast initially. So to do the focusing, we initially move the sample up. So what we are looking for autofocus, first we have to find a good, a bright circular spot.
This is manual focus, and then after the system will do automatic focus. We need to position, we have side view and top view. We need to position top view inside of side view, and then the system can do the automatic focus.
Contrast? How will it work?
But
What if there's not enough contrast?
no, the system can do it. It can do it contrast. Yeah. You will see normally he will do it. You know, at the focus, the system will moves up and moves down, and will find a good position.
So let me go a bit behind first.
At the initial stage, so you have fed Poisson's ratio value.
Mhm.
So suppose if there is a new alloy development for which I don't know.
0.3 will
0.3.
What you can do, Kamal, you can.
Yeah.
Could you please show me the software? I will give you a tip that can help you to do easily the. You need to remove in the right part of the software. You click remove auto brightness.
Yeah,
remove it.
auto part. Yes.
Okay.
Now I
And
remember.
move to it's minimum, and no, this one in minimum, and side view in minimum. Okay.
Sorry. Yeah.
And
size
zoom,
should be
and no, that was good, I think. No, that was good. You can just put zoom at 0. The zoom value, it must be at 0. 0. No, 0. Now you are in maximum zoom.
Opposite side, yes. Sorry. Yeah.
And now again, the brightness, you need to put it in maximum. The second cursor, or the third cursor. You please try. I will let you know. Try to put it in the maximum. This is minimum. Put it in the maximum.
It's in maximum only. Now
No.
we are like minimum.
No, in another side. Okay, okay,
This side,
okay.
left side.
Now you have to move to the center of this circle.
So
This is the easier way. You go to the center of this circle, and when
And-
cursor is in the center, go to the center, go to the center. No, a little more, a little more. You must be in the center of the circle, and now you click on set brightness, set autofocus.
we will make it auto and
No,
we'll
no, no.
click on-
You need. Yeah, this is the system.
This is fine.
Autofocus. Now you can zoom to the surface of the sample. Zoom, and then you
So-
click on auto brightness and zoom.
Yeah.
Auto. You click on auto.
Yeah.
Auto brightness. And zoom. Zoom inside. You didn't click on auto brightness. Auto brightness.
It got checked.
Yeah. And now you are good.
Yes. We can do this, or because we had that circle, I think we can just click on auto continue here also on software. So it should do the auto zoom also for us focusing. So we will click. So after finding that bright spot, basically we set it to those, and then we can just click on auto, and the system itself will do the focusing for us.
The ring to establish a plane.
Which ring?
The ring around the.
You will say the reference ring, the reference fork. Reference fork is for MCT. You can remove it also. For some kind of the sample, if you don't need the reference, you can remove and do the indentation without reference. If you will do the conventional hardness, you don't need the reference. But for instrumented indentation, as we measure the exact value of penetration depth, we need the reference ring, because reference ring will touch the surface, okay? And when the reference ring touch the surface, then indenter starts to move. And we measure the difference of the penetration depth between the position of reference and the position of the indenter.
The reference is the 0 point.
The 0 point for us is the reference. This is why we need it. And why this is important, because if we have thermal expansion, the sample will move up. But as the reference is in contact with the surface of the sample, the reference will move up. So you will remove any influence of thermal drift from your measurement.
What is the kilometer? The ring is a big.
The internal diameter is 8 millimeter. So you need to have a sample bigger than 8 millimeter.
Okay, and the ring may not be perpendicular to the axis.
No, the ring is perpendicular, because the ring has two forks, and two fork must be positioned at the surface of the sample. This is not only one fork, this is two fork. This is a ring with two fork, and the two fork will be at the surface of the sample.
Here you are doing flat sample. Suppose I have a coating deposited on some sample, and I need to do, suppose, at the cross section.
Yeah, you will mount, polish, and you will do.
Okay.
That's the only solution that I have. Okay.
Okay, so we can see it's focused. The surface area, if we feel like it's not, we can still slightly move stage up and down using the arrow keys if we want to. Then comes where to do the indentation. So we look for a clean surface. Now thing is, let's select our reference. So we have these options here, multiple, if we can see, like single point. So if we want to do indent and we don't have, say, a very clear surface or flat, and we see patches of good areas, we can have this option, select the point what I want to do. So say, for example, I want to do ADO first. So these are like my parameters for doing the ADO, automatic depth adjustment, basically. So basically this is, while doing this using combined with reference ring, we are finding where the exactly my surface is there, and as you can see, this is done with a very small force, so we won't be anyhow damaging the surface area itself also. Then further we can define our approach speeds. So basically, and approach percentage, the importance of that is basically, say I have a hard surface if I go slowly, still I can find my surface very easily, because the change in the stiffness and all will be very good to a high value. But say for example, I have a soft coating. In that case, we may increase the speed more, so that if I have a small soft coating, basically it's something like say skin, I am going quickly, it will detect that penetration faster, and it will be able to detect that thing that my surface has been achieved. But say for example, if I go very slowly and slowly, it won't able to detect, it may not detect exactly on the surface point, but may go bit beyond. So that's why generally when we want to do for soft surface, it's better to increase our approach speed, do it bit faster, so that we detect it more accurately. So let's do ADO at default only. We can set a reference point, like by clicking, if we see here the cursor, I click, it sets my reference point to that per surface. So now I have a coordinate set also, say 0 and 0 0 there, and if I go there, so in this way we set our reference, and then let's say an example more, I'll do an ADO. If we want to do ADO, we have done the ADO now here. We set a reference 0 0. At this point I want to do ADO. Now let's say I want to do indent. I'll want to do it here. I'll click. Then we can select what type of measurement we want to perform. So quasi-static is basically what we do, the normal indentation load. Then we have multi-cycle mode, where we can do multiple, in a cyclic way we can give the indentation load and do multiple up and down and full cycles of indentation. Then user defined, say to a particular load, then pause, then a load, then pause, then say unloading, then again load. So something like that. Depending on that we can set the things. So let's here we do the quasi-static. Then again we have different options. Linear load, load will be applied in terms of linear. Again under that we have option, that how we want to apply the load. Do we want a load control, or we want a depth control? And then we can set maximum load, our loading rate, example same pause, for which we want to pause at the maximum load, and then the loading rate in that. And if we go here, these are the speeds which we were talking about, I was talking about, our approach speed, contact stiffness, and all those parameters we can change from here. And we can change even the load ranges if required. Say for example, I want to do the want to go a bit higher range, we can select that, or we can change the depth range of our sensor, we can select from here. So then we have quadratic option, say we want more readings, or I want my load to vary in terms of square. We can see the load profile, we can select this. And if we want a constant strain mode, something like this, basically we want more point during the lower values, we can go with constant strain also. And again same way we have other options, depth control or load control options in each of these options there. So let's go to next. We will go via load control only. Let's set. Then we have set the loading rate. Say I'll put it like 1000 millinewton. Say I want to set my depth by maximum what type depth till I want to do. So when the depth is good, it will basically stop the loading. So we have set 0.1 and let's click. Okay, so we see we are missing something. Software will give you pop-up like we didn't put the unloading rate. So we will put the same unloading rate of 1000 millinewton and let's click OK. Now this is one. So if you want to do a full profile or linear, we have other options also, like you can go for in a straight line. If you want to measure, we select this, we stretch it, and there we can tell what we want. So we want spacing, that after this much spacing an indent should happen, or we can define it as per counts, that in this much length I want these many indent, or we can do it basis on both, that at this much spacing I want these many indent. So let's say for example same, we click it, select and click populate, then again it wants what we want to do. Say we want to do quasic, we just click OK. So you can see it has populated 9 indents which we initially put, and we can do, if we want to change the spacings again, we can just click and drag. So I want something like this, I want this, I want to. So it's very easy to do our custom indenting on the surface as we like. If we want matrix, same way, we can click on matrix, click on the region. It's populated, too populated. So if we want to remove, we can click here and click remove the measurement. So that is gone. Let's remove this first AD also, which we selected. So if I want to populate a matrix, basically we select that option, we click it, select the area like line, then again we tell it to populate as per our requirement, click populate, tell it, and it's populated. And again we can resize our matrix anytime we want, just drag and drop. So automatically it adjusts, because we had set it as per spacing, so it has introduced more indent. If it has been introduced based on say counts, count would have remained same, basically spacing would have changed. So let's remove this also, and we click on the start indent. So basically what it will do, it will do an ADO at this point, then it will do an indent as per our set instructions to this point. So we click start. So you can see, if you see now, stage will go down first, then it will move towards to the under the indenter as per our reference and carry out the ADO and then indentation. And as the ADO is successful, we should see a green sign here also. So we can see it's again same, sample is going to move. So it's warning us that nothing should collide. So we know nothing is in the movement. So we click OK. And now stage is moving under the indenter, and it automatically stage will go up near to the indenter. And to see the ADO corresponding, we can see Z table approaching when it is moving up, and we can see at what sequence here again. So currently Z stage is moving, then we will go indenter. So we can see it has starting to do the in contact. Now indenter is approaching the surface. So our DZ would fine, else it would have given us a pop-up like in Scratch. So we can see it's basically a fine adjust indent only what we do ADO. But this gives us another benefit is if ADO is happening correctly or not. That itself also gives us an idea that our indenter is positioned perfectly or not. So if for example I don't get a good ADO curve or that curve, that itself is indication that my sample is not mounted properly. Because when it is properly, say it could be tilted, or say for example indenter has approached before the reference ring. So there could be various things. So accordingly we can check and tune our things. accordingly and place the make the sample placement more accurate, so we get the idea. So now our indentation is started, so it's stabilizing the system, and then our measurement will start. So at a time itself also we can see the parameters here, what we put it for the measurements, and corresponding what number of indent or measurement it is proceeding. So we had currently 1, so it is showing 1 of 1. If we had multiple, it would start increasing correspondingly the number as the indent starts. Oh, what happened? Video. Oh, something happened. Maybe location was not that good. So we can see maybe we thought the location was good, but it was not, because we can see we don't have a good indentation curve here. So let it do. Something happened, I don't know what. Let's see at the surface. This should give an idea what might have happened. Oh. So we didn't focus also properly. So we can see basically, yes, we cannot see an indent, which was our aim. So something definitely was amiss. It's clear from here. So what we will do, let's try to do another indent for that. So we'll just finish it. Yes, the surface is clean and everything. So if we want to do another indent, we just click on the indenter. So let's do the focusing again. Bit, we will do entire process again. We'll click on start focus, let the system do. So we are at center, we click OK.
Yes.
zoom into the area again. So let's set the reference here. We'll do an ADO here again. Then, yeah, we will do an indent here. Let's now max load. Say for me. Okay. Now we will try with this.
LVDT sensor, yeah. For MCT, LVDT. For some of the instrument, we have the piezo, yeah.
Yeah. So here Shomik itself told me what happened. So you know he got well good trained. I trained him well. Basically in previous measurement.
Komel, could you
Yeah.
just check if the system is in the indentation mode for ARM? This is not in a scratch mode?
It's indentation. What actually happened, we had a depth control and I didn't check the value was too low.
Okay.
It was like 0.1 micron. So the moment
Okay.
it reached that, it stopped.
Okay. Now you can use load control.
Yes. Yeah, so now I switched to load control. I have put like 1 Newton load, so we can do. So the issue was in depth control because the depth we set was too low. It was just 0.1 micron. So the moment it reached that depth, it stopped the measurement because
because
it has
the system will keep this penetration depth here.
Yeah. So we got another idea. We should be careful while checking everything. If we are doing values are should be, and this is another indication that something was wrong. So we can always look because ADO was perfect, everything was perfect. That means something which we put in parameter basically was wrong. So that is how we can adjust things from our data also, how to do the things. So again, we can see ADO is very good, and now we should be able to see a very good indent. So basically, if there I had a more penetration depth set, say 10 to 20 micron, we would have got the indent. While indent is going on, we will discuss few things while doing the indentation from instrument point of view. The important thing is, especially like for scratch also, that our calibration should be good. Calibration of head to our microscope. We can determine it immediately if calibration is off. For example, I am doing scratch and I see my scratch starting point is not that, say the view which it captured, it was the first point it started capturing from chipping point or somewhere else, or scratch is not visible. That itself is an indication that my microscope to head distance is off. So there we need to do this calibration again. It's very easy and we can do it with copper indent. Basically we do an indent, find that indent and see if it is coming under microscope or not, or we adjust the coordinates accordingly, find that indent and give it an idea. The other important thing is when comes is the indenter calibration. So once I have a indenter, like during installation, the service engineer has done the calibrations for all the indenters. So when we talk about indenter calibration, basically what we do, we take a standard which is fused silica whose elastic modulus we know. So in a way what we are doing reverse calculation because we know its elastic modulus. We find out what's the value of my indenter surface area is. What my indent surface area is, because that we do need to know indenter surface area when I want to find the hardness. So in this way we get to know the exact surface area and then we proceed for indentation. So basically how to in a way, the way to check my indenter there position, if it's well calibrated or say something is not damaged to the indenter where we cannot see the indenter image also, what we can do, say this is my standard BK7. So we know its elastic modulus, we do the indent, check the value if elastic modulus is coming correct or not. If it's not coming correct, it's way off. One reason could be my indenter is now damaged and I need to replace the indenter. That is very easy way to do. Other is we can just take the indenter under the microscope and see it. And if say I came to know it's not very off, it's slightly off, maybe it's not that major concern, then what we can do, we can again do a new indenter calibration so it gets as per new surface area. But most those are one of few the important things here in terms of indentation. And for calibration part, in instrument part itself, software also tells you that everything is calibrated. When we see this green light here, that basically means everything is well calibrated and instrument is perfect to work with. So you can see indentation is going on, a beautiful very curve is coming. Meanwhile, let's have a look at the options of indenters which we have, or say standards. So one is copper, we have already seen, it's not a standard, just a reference sample. Then we did on ALN scratch, that is again a reference sample. But in terms of standard, we again have two things to check. So we have this BK7, then we have steel standard also to verify if my instrument is well calibrated or not. Then coming to indenters, again you have multiple options. So I'll keep it. I don't want it. So here what we have is the Rockwell indenter. You can see chronicle. So this one is a 200 micron indental with Rockwell C. We can see its alpha angle is also 120 degree. I'll put this back for safety. We don't want it to get damaged. So similarly, you have another Rockwell C and it's 100 micron, and so basically we have here two. There similarly we have here Berkovich indenter also if required. Then you have here the Vickers indenter also. So currently which is mounted here is a Vickers indenter with which we are going. So as you saw, it's very important when we are doing any kind of indentation, because in indentation basically it's all the, what's the thing is, it's about surface area and height. And so if we have chosen a wrong indenter and doing the measurement with that, definitely all the calculations will go wrong and we will have the wrong readings. So if we are changing the indenter, say I am going from Vicker to Berkovich, it is very important that we make the correct selection and change the indenter option in the software so that it knows that now I am not doing the Vicker, I am doing via Berkovich, and it's obviously its area of contact will be different so that we can get the correct readings values. We should have maybe done with more loading speed, it would have been a bit faster. Yes.
How much is the loading rate and unloading rate?
I think it's 1 milli Let me check. It's 100. Yes, it's way low. 100 millinewton per minute.
Normally you have your maximum load is 1000 millinewton. So loading rate must be 6 times of maximum load. That means
Maximum.
6000
Yes.
millinewton per minute.
Yeah. So basically, because again same thing, we didn't check the loading rates. They were on default, and we proceeded with that only. So this will take bit
Yeah,
time. We are
will
almost at half.
Mhm. But we have the document. The name of this document is recommended parameters and troubleshooting. So with this document, you can see as a function of type of the sample and the test that you will do, you have some recommendation to say which value of load you have to select, which value of the loading rate. So this will help you to select the good parameters.
Yes. So that is important. If you don't know, you can go through that document because it gives you a starting point, basically, that document. So that document is both for scratch also. We have same, it's for indentation. So that really helps in setting, will help you to get the starting parameter. Then as per the sample, we can tune the values and you can get the more refined data. Yeah. So let me show you the document. If I remember, I had it on the desktop itself. Meantime, yeah. So here it is, the document which he told. So this is the document for Scratch. If we go through below, you can see everything in general, like recommended parameter. If we browse what type of coating, say we have hard coating on hard surface substrate, we have soft coating on hard substrate, or say metallic. So correspondingly, you have everything initially to start with, depending on our different even product lines, because it's a common document. So like here we have RST. So like this is a good speeds if we have a hard coating on hard substrate, and on using MCT we can start initially with these parameters like that. And similarly, all those things like scratch, what soft, how it looks, or say certain things, if you are not able to look at the things, we can do those also. So like say for example here, you are not able to observe any kind of critical load. So these could be in general the issues, and this could be their corresponding solutions. And like this is how to check our indenter is good or bad. So one option is, as I told, we can look under the microscope and have a view and see how things are. Or say in Scratch also itself, you can get an idea by seeing how your Scratch image is coming, looking at. So you see these marks coming, it's not proper, that's another an indication that indenter has been damaged. That say these fine marks, this. Similarly, we have an option for indentation. Yeah. So let's go home. So here we can have again, so like we did ADO. So what should be, what ADO does, what its parameter, approach speed, as we were discussing, every those things we can do. So our case, MCT case is, don't go it's basically MST, or you can see in bracket we have written. So these are ones which we have to look for. And if we go below, like these are ADO parameters depending on what type of instrument and stiffness, depending on material style. For example, this is for hard coatings. Then if we have polymer or soft coatings, we can work with this. Then again, say ADO is not looking good, what could be the issue in general? So it's a really good document to give an idea if you are stuck somewhere, things are not happening, you feel like data is not coming correctly. You can always go back, refer to the document and tune your parameters accordingly to get the data out of the surface. Like for example, we discussed about Poisson ratio, right? So for example, it even gives you an idea what type of Poisson ratios values we should know in case we don't know what the Poisson values are in that. Same for like thickness, it should that's the general thumb rule, it should be 10% of your film thickness. How much distance should be there between two indenters, different rates. Likewise, we can go through it. So I will recommend someone who definitely is coming first time for measurement, you can go through this document to give them to give yourself an idea, and second thing is to give an idea to the operator also, because his operator also has to start from some point. So if you have an idea, you have definitely he will be able to carry out your measurements very quickly and you will get the results very quickly also. Moreover, thing is, say you have small or very thin sample, when we are doing the testing, definitely it's kind of a destructive technique, because we are doing scratches, we are doing indent impression. So some part of, again, wherever that trial measurements are being happening, basically now that area is out of picture for doing the next measurement. So that's why having some idea recommended values to start with is a really good option to start your measurement. So this document is available here. You can contact Professor Amitava Ghosh to, if you don't have for that, and if you want to say check about instrument, it's working, definitely before you come again to sir, I always recommend go through the manual. You can should ask him first the manual, go through it, get an idea, because that also will give you an idea how to do the measurement, what you take out, because manual also is very self-explanatory, very detailed, and it also gives you an idea about the different things which you can do further with the instrument in detail. So you know what type of studies you can do further, or to how to extract the most out of your instrument, so that you can have a good, more accurate values and study. So yeah, we are pretty good now. Yeah, now because we are done with the loading, we can see now unloading is happening. So I think within couple of minutes it should be over. So like for example, we can do these adhesion test also using indentations of measurements. And here also we have the optimization option, not this. Yeah, this is another point we will go through. In case we will need to refine the contact point, software does allow us if we feel like contact point is not here. So this is another example of how to detect your indenter is damaged by just doing the indenter thing. Meanwhile, if anyone has any questions, doubt, you can always ask, because we have to wait for it to complete to see the indent. So this is for Beaker. Similarly, because you have Berkovich, you can have a look at Berkovich. Yeah. So in this way, you do for on standard like fused silica, and you should be able to see the difference. So that indirectly is a way, because your elastic coefficient will change. So that will give you an idea, yes, indenter is damaged and we need to change it.
Okay, so.
Komal, we can wind the session.
Okay, sir, fine. So what we can do, if required, we can do an immediate unloading also required. So you have this option, let's try it. Let's we click. So what it will do, basically it will immediately start unloading the sample. It will take from that position only now. So let's say cancel. Yeah, because it's
Unloading rate normally must be 6 times of maximum load. So
maximum.
selected very low value for this.
Yeah.
It's okay. I think.
Yeah, because indent is there, we should be able to see the impression itself clearly. So, okay. Okay. So we go here. So if, for example, if we want to edit the contact point, we can click on this arrow and all, and we can just select the point. Basically, point of inflation is our contact point. So we can see it's almost correct. And that way we can do. Again, we have analysis window where, like in Scratch, we can see all those data. Same thing we can do here. Here you have more thing. If you have group of sample, you can click on this to get an idea of the comparative chart. If we have done the mapping, you can even do a Gaussian fit to find out how the things are by just going in tool and clicking here the Gaussian fit. So it does as per area, run the script and give you a Gaussian area for the indentation. So here we don't have any matrix, so it gave us bit an expansion. So this is in general all about our MCT and how to do indentation. And Scratch part doing on MCT is entirely similar what we did on RST. The only thing is, because we have automated stages here, we don't have to manually move along the Z or say along the X-axis, because system itself will do. Okay, I think, yeah, that is all for, I think, demonstration we have. So any questions, if you have, you can ask.
This is okay, Komal, because they have asked several questions during your talk. Yeah.
Yeah, so it's fine. Thank you.
Yeah, I think the people get tired now, so we will.
So, Dr. Kamal, this is Amitava here from this MSB 304. So I think I must thank you, and the mere thanks is not enough for you. Last 2 hours you have been continuously supporting us from the venue, and I think they are very much helpful. They got enough benefit out of it. They came to know what about the scope of these things. And to be very frank, initially we were thinking about a personal visit, but for you people, it is already there in-house, so you can just make a plan and go and visit. That's not a problem. It is there open. Regarding the facility to be made available to you, it might be from January onwards. There would be central portal. You can book it, but there will be small charging because just to retrieve the maintenance cost of this machine. Okay, that is anyway. It's very nominal.
Also, the indenter's cost is important.
Indenter cost is very important. So that depends again how frequently you use, and in very specific cases you can have your own indenter also. Anyway, nevertheless, big round of applause to Dr. Insightful things. And
Komal also.
And to Komal and the team, and Ganeshan is the driving fellow actually majorly. He has driven the entire thing to make this workshop happen and finally getting concluded successfully. So thank you once again. Thank you.
Thank you, everyone.
Right. So one more thing is that if you have any specific question, we'll just float a Google form. Maybe we'll collect those technical questions and give a feedback also. But technical question, we'll forward it to Dr. Yazdi. If there is very specific we cannot answer, then we'll get it from him and we'll get back to you. I hope you have all enjoyed, including the food. We tried our level best, whatever facility we have. We have tea and little refreshment outside. So just enjoy it.
Thank you so much.
Yeah. Thank you, everyone. Thank you, sir, for the opportunity.
So what is the surface preparation for scratch tester? So as spray coating, I can go and do it, is it?
Yeah. If you don't have a very rough surface, you can do it.
So if RA is around 6 microns, then we can go ahead because the inductor is 200 microns, right?
This is the radius of the 200 microns.
Okay. So we have to look for RZ or RT.
Yeah, RI is important.
Okay.
You can check your RI, but if not, you can.
Threshold for the RA?
No, this is not really for. In addition, we have. This is better to have a maximum 50.
See, if your surface is too rough,
nanometer.
might be you can polish it and do.
Yeah, you can just polish it.
Okay. But say, for example, the addition is not good, then